The aim of Assessment Task 4 is to develop our turbine design further from AT3. This task involves in analysing how the research from AT3 will perform when undergoing bending, deflecting and shear forces for both the tower and the blades. The calculations will involve a wind force, thus meaning the calculations would be more involved. However, an evenly distributed load can be used from the wind to simplify calculations. Task 1 aims to produce an analysis report based on the bending and deflection of the final design, which was optimized in AT3. Moreover, Task 2 involves in developing an optimized design based on shear and bending forces. These aspects can include cross-sectional area and material selection. For Task 2, a basis is already developed from AT3, however a more refined design is to be created that must be able to comply with the requirements whilst also being relatively environmentally friendly by, for example, not overusing materials. The requirements for AT4 that stakeholders would like to see is highly relevant and accurate research and optimization in order to see a design that has reasoning and justification and evidence that shows that the design will comply and, most importantly, be safe for others. For this task, we must stay within the gale force of 24.5 to 28.4 meters per second from the Beaufort scale. We also have to develop a set of requirements for axial deflection, shear force requirements, and bending requirements. As like said before, the turbine has to be safe, and it also has to be able to perform to a standard where minimal stress is put on components to maximize life and longevity of the parts, whilst also decreasing maintenance on the turbine. In order to address these constraints, our group will advise to go through extensive research and analysis to compare material and cross-sectional properties in order to achieve these constraints to a reasonable standard above what is expected.
Thanks, Jacob. A uniformly distributed load, or UDL, is a load that spreads evenly across the length of a structure, such as wind pressure along the height of a wind turbine tower or the length of its blades. In the design of wind turbines, understanding UDL is essential because it directly influences the forces that the structure must withstand. When wind acts as a UDL on wind turbine blades, it creates a consistent load per unit length, leading to bending moments that increase towards the roots of the blades, where the stress is greatest. Similarly, the tower experiences a UDL from wind pressure, resulting in peak bending moment at the base. Accurately accounting for UDL in design calculations ensures that the wind turbine can handle these forces without structural failure, enhancing its reliability and performance under varying wind conditions. The distributed wind load on the tower is calculated by a half times air pressure times the velocity of wind squared times the width of the tower, with air pressure being 1.2 kilograms per meter cubed. Bending moments are internal forces that cause a structure to bend when subjected to external loads. In wind turbines, bending moments are particularly significant for both the blades and the tower. As wind pressure acts on the turbine, it creates bending moments along the length of the blades and the heights of the tower, with the highest moments occurring where the structure is most constrained, which is the roots of the blades and the base of the tower. These areas are critical because they bear the most stress and are therefore more prone to potential failure. Understanding and calculating bending moments is crucial for designing a wind turbine that can withstand these forces, ensuring that it remains stable, safe, and efficient during operation. Proper design accounts for these moments, allowing for the use of materials that provide the necessary strength without excessive weight or cost.
When selecting materials for the components of your wind turbine in Assessment Task 4, it is critical to consider the forces induced by bending moments and what materials are equipped with the properties to manage them. Bending moments and beams induce three internal reaction forces that attempt to counter the flexing of the member. These three reaction forces are compressive force, tensile force, and shear force. Within the tower of the turbine, while still managing the axial compressive loads instigated by the weight force, the tensile and compressive loads applied by bending moments increases the need for ideal material selection. While the tensile force due to bending serves to counter the compressive weight force of the tower, on the other hand, the compressive force generated by the bending moment adds to produce an even larger compressive force on one side of the neutral axis. The blades of the wind turbine face a similar scenario, however varies in that it is dependent upon the orientation of the blades in its rotation, and the forces being summed are both that of the weight force and the centripetal. In order to deal with the increased and complex loads formed by the compounding of these different stress scenarios occurring simultaneously, it is ever more critical to perform calculations of the total loads, followed by selecting material that is extremely capable in either tension, compression, or both, dependent on the situation. In managing the forces generated by bending moments within the wind turbine's components, alongside material selection, cross-sectional geometry is another key aspect of design and engineering to utilise. Principal to the concept of bending moments is that, as examining further from the central neutral axis, when a UDL is applied, stress increases linearly. As such, in the case of the wind turbine, it is logical to strengthen members undergoing bending by placing material away from the low concentrations of stress closely surrounding the neutral axis where it is not needed, and instead further outboard where the stress is higher. Whilst it may be simple to move material away from the neutral axis, it is also important to consider how that material mass is distributed. With the wind turbine's tower, for example, where compressive forces are largest, it would be safe to say that most would presume material needs to move to the compressive side of the neutral axis. However, if the chosen material features a relatively low tensile strength, reducing the cross-sectional area of the side of the member in tension may result in failure when undergoing a significant bending moment. This should encourage the exploration of not only members with hollow cross-sections to move material outboard, but also asymmetric profiles that move strength to a particular side of the neutral axis, only if better suited to the capabilities of the chosen construction material.
When preparing for AT4, it's essential to approach the design process with a critical and analytical mindset. Start by thoroughly understanding the concepts of bending, shear, and deflection, as these will guide your evaluations and optimizations. Ensure your calculations are detailed, accurate, and backed by clear assumptions. Using free body diagrams can help you visualize forces and simplify complex problems. Additionally, don't overlook the importance of considering potential failure mechanisms and how they could impact your design. Even though this is an individual task, discussing these ideas with your peers can offer new insights and help refine your approach.